please hit subscribe.
The first trick that we'll look at is checking the differences between the terms as n approaches infinity. The intuition behind this approach is as follows. If we know that the sequence is convergent, then we know that the terms approach the limit L. And if the terms approach the limit L, then two consecutive terms will also get closer and closer to each other. So if you just write that down, we say that if we know that the sequence converges, then the limit of the difference between these two consecutive terms is 0. However, we see that this is not very useful because in order for us to actually have this conclusion, we need to be told that the sequence is convergent. However, what we're looking for is actually a test so that we can say whether something is convergent or divergent. And here, this is not yet the test because this is the information that we have to have before we can make this statement here. However, we can actually take the contrapositive of this statement. So let's recall that in logic, the contrapositive is just switching the conclusion and the hypothesis and negating them. So in logic, we know that the contrapositive is equivalent to the statement itself. So if we write the contrapositive of this statement, it will read as follows. If the limit as n approaches infinity of the difference between two consecutive terms in the sequence is not 0, so that is the negation of this bit here. If it's not 0, then the sequence does not converge. So that is the negation of that part here. And does not converge means it diverges. So this is the contrapositive. So what that means now is that this statement is equivalent to this statement. So if this is true, then this is also true. However, the contrapositive looks much more useful because now we are told that if we know this fact, we can make this conclusion of divergence. Therefore, this is a divergence test, a test for divergence. So we will just need to compute the difference between two consecutive terms and get the limit. And if that limit is not equal to 0, then we are told that we can conclude that the sequence is divergent. So this is useful as a test. And because this is useful and we will be using it in the future, let's try to prove it here. So to prove this statement, we either prove this first one or this second one because both of them mean the same thing. They're contrapositives of each other. So the proof is easier if we choose to prove the first one. So the proof goes as follows. First, let's write the hypothesis that the sequence is convergent. So the sequence converges means that the limit L exists such that this limit holds. This limit statement holds. Now let's just compute this difference here, the limit of that difference. Now we can separate that into two limits because we know that the sequence is convergent and therefore this bit is convergent and this bit is also convergent. And so we now have this, and we can just modify the variable here to n plus 1 because as n approaches infinity, we know that n plus 1 also approaches infinity. And now we have this form. And now the reason we wanted to make it into this form is that now this form is the same as this form, right? N plus 1, n, and therefore they will have the same limit. And so the limit here is L, and the limit here is L. L minus L is 0. And so we have proven the first part. We have proven that if it is convergent, so we use that information to allow us to separate that into two limits and to actually show that this limit is L and this limit is L. If it's convergent, then that difference is 0. So that's the proof. Now let us look at an example using this test. So the example we will be using is the sequence a sub n equals n. Does it converge? Using this test, we cannot really know. This test does not tell us whether a sequence converges, but it does tell us when a sequence diverges. So we have to check this condition, and if this is satisfied, we know that it diverges. However, if this is not satisfied, it does not mean that the sequence converges. So all we can tell from this test is that if this is satisfied, then it diverges and nothing else. And because we don't answer a question of convergence here, we cannot really use this test to know if this sequence converges. However, we can ask the question, does a sub n equals n diverge? And that is yes, because we can use this test now. So because we know that the limit of the difference here can be written in this way, so a sub n plus 1 is just n plus 1 and a sub n is just n. So when we get that limit, that's the limit as n approaches infinity of 1, and that's just 1, and it's not 0. And now we have satisfied the hypothesis, and it says that if it's not 0, this limit is not 0, then it diverges. And so we can answer this question, it diverges. And because we now know it diverges, it does not converge, because divergence is just the opposite of convergence. So if it does not diverge, it converges, and if it does not converge, it diverges. So in this case, it diverges, and therefore, it does not converge. Now let's take another example. In this example, we will be using the following sequence. A sub n equals this sum. So this is being summed from k equals 1 to k equals n. And this kind of sequence has a special name. It's called a series. So a series is just a sequence whose terms are the sum of terms of another sequence. So in this case, the terms of this series are the sums of the terms of this sequence k cubed. So a sub k equals k cubed, and then we're summing it from k equals 1 to k equals n. So yeah, yes, this is what we call a series. And now, does this series converge? Again, the answer to that is we cannot know by using this test, because this test only tests for divergence. If this is satisfied, then it diverges. If it is not satisfied, we do not know. So we cannot say it converges. We can just say we do not know. So let's ask the relevant question. Does the series diverge? And the answer to that is in fact yes, because if we compute this difference again, so the limit becomes like this. So here we have n plus 1 as the last term. Here we have n as the last term. And for those of us who may need to review this summation notation, I'm just expanding it here more clearly. So this term here is retained here, while this term is broken into two terms. The term up to n and the n plus first term. So this is the n plus first term, and this term is just the terms from k equals 1 to k equals n. And this term cancels with this one, and we are left with this limit. And we already know that this limit approaches, or rather is infinity. So this sequence here approaches infinity, and infinity is not 0. And therefore, we can conclude that this sequence actually diverges. Therefore, it does not converge. Let's take a look at another example. In this example, we will be using the following series. And again, if we ask the question, does this series converge? The answer is we cannot use this test to directly answer the question. And what we can do is answer the negative. Does it not converge, or more easily, does it diverge? And in fact, the answer is yes. We do that, we get to that answer by actually computing this expression here. That's the limit of the difference. And when we do that, we obtain this expression again. It's just the series, the difference in the two series here. This one is from k equals 1 to k equals n plus 1. And here, it's only up to k equals n. And if you've done enough of these subtractions, you'd notice that, in fact, this subtraction is such that the answer is just the n plus first term of this sequence here. So the n plus first term is just n plus 1 all over n plus 4. And if we take the limit of that, as n approaches infinity, we obtain 1/4. Which is not equal to 0. And therefore, this is satisfied, and we can say that this series diverges. Now we look at this example. It's a simple example, a simple sequence. A sub n equals the square root of n. So this is not a series, it's just a simple sequence without the summation here. And again, the answer to that is we cannot know just by using this test. We cannot directly know, so we have to ask the other question, does it diverge? And using this test, we also cannot know. And that's because when we compute the difference between consecutive terms as n approaches infinity, so let's just write it here, that's the square root of n plus 1 minus square root of n, and we multiply the numerator and the denominator by the conjugate. This is the conjugate, and we get a limit that is 0, and therefore this is not satisfied. Now, if this is not satisfied, we cannot say whether it converges or diverges. And in fact, we already know from intuition that square root of n actually diverges, right? Because as n gets bigger and bigger, actually its square root also gets bigger and bigger. So from intuition, we know that this diverges. And when we compute this, we actually get 0. And therefore, it is not true that if it is 0, it converges. So we say that the converse is false. The converse is, if this is true, then it converges. So we have shown that it is false in this example, right? This is the converse. If this is equal to 0, then the sequence converges. And we know it is wrong, because in fact here it is equal to 0, and yet we know that this sequence actually diverges. So from this test, if this quantity here is not equal to 0, we cannot say anything. But if it is, or rather if it equals 0, we cannot say anything. But if it does not equal to 0, we can say that it diverges. The final example that we will talk about in this video is this series. It's the geometric series that is quite common, so probably you're familiar with this. And in this question, we're asking if it converges if we have r between 0 and 1, and if we have the first term not equal to 0. Because if it were equal to 0, then all the terms of our sequence and series are just 0, and so it will converge clearly. But if it's not 0, and our r is between 0 and 1, does it converge? And just by using this test, again, we cannot know directly. We have to ask the other question. Does it diverge? And again, let's try to compute that difference. We see that, so again, we do this difference here. We're left with this. And because alpha is not 0 and r is between 0 and 1, this limit actually approaches 0, right? And because it approaches 0, we've shown previously that we cannot tell if this diverges or converges. So there's no information we can get from this test. But we also note that if r is greater than or equal to 1, the series actually diverges. And that's because when you do the difference there, so this is the difference. So that difference, if alpha is not 0, then that difference is alpha, right? Alpha times r raised to the n. If r equals 1, if you substitute r equals 1 there, then what you get is alpha. And alpha is not 0 from the condition here. And because it's not 0, then it diverges. So it diverges if r equals 1. And if r is greater than 1, we look at this part here, this term r to the n approaches infinity, and therefore this expression approaches infinity, and infinity is not 0, so this statement is satisfied, and therefore the sequence diverges. So if r is greater than or equal to 1, this series actually diverges, and we can tell that using this test. But if it's less than 1, we cannot know anything from this test. In this video, we develop a test to determine whether a sequence diverges. We have made use of the intuition that the two consecutive terms in a sequence as n approaches infinity approach the same number, the limit L. And so if they approach the same number, they also get close to each other. And so we've intuited and actually proven the following statement, that if the sequence converges, then the difference between two consecutive terms as n approaches infinity, the limit of that is actually 0. So we also made use of the contrapositive of this statement, because this statement alone does not give us a test. But the contrapositive gives us a test. It gives us a condition that we must satisfy to be able to determine that the sequence diverges. And that condition is that the difference between two consecutive terms in a sequence must not approach 0. And that is just the negative of this part. And if it does not approach 0, then the sequence diverges. And again, this statement is just the negative of this bit, so that's the contrapositive. And while this statement is true, and we've proven that, we have also shown that there is a counterexample for the converse. So the converse of this statement is false. The converse is that if this statement is true, that the difference between two consecutive terms approaches 0, then the sequence converges. We've shown that this statement is false. It does not hold, and there are counterexamples for this. In the next video, we will continue to look at this intuition about two consecutive terms in the sequence, but we will be looking at the ratios instead of the differences.